This question has us draw two different reaction coordinate diagrams, and we're given the values of delta G reaction and energy of activation for the forward reaction. So for the first one, AB reacts with C to make AC and B. We're given the value of delta G reaction as plus 3 kilojoules. Remember that delta G reaction is going to be the product energy minus the reactant. My reactant starts at 0 kilojoules. So if I add a plus 3 to my energy scale, then my product energy, which is A bonded to C with B no longer bonded, is going to be 3 kilojoules higher than my reactant. I'm also told that the energy of activation for the forward reaction is plus 7 kilojoules. This is going to be the difference in energy between the transition state and the reactant. So I will put on my energy diagram a mark for 7 kilojoules, and as the reactant goes to product, it has to pass through the transition state. So we will go up the hill on the way to the transition state, and then down the hill on the way to the product. Now let's try this for AB reacting with D to make AD plus B. This time, delta G reaction is minus 4 kilojoules. So if my reactant is at 0 kilojoules, let me put a mark on my scale at minus 4. So my product energy this time is lower, where A is now bonded to D, with B no longer in a bond. My energy of activation is 5 kilojoules, so let me put a mark at 5 on this scale, and the transition state is going to be at this energy level. So when I go from reactant to product, I pass up the hill to get to the transition state and down the hill now to get to the product. So that's how we make our diagrams. Now we have some questions about our diagrams. The first one asks, if delta S for each reaction is close to 0, which diagram represents an exothermic reaction and an endothermic reaction? So essentially the energy of these diagrams, which is the Gibbs free energy, is delta H minus T delta S. And if S is close to 0, then the energy reflected in these diagrams is going to be close to delta H. We know for an exothermic reaction, delta H is less than 0. And for an endothermic reaction, delta H is going to be greater than 0. So let's go back and look at our diagrams. Notice that diagram 1 goes upward toward the product. So when I take product minus reactant, I am going to get a plus value. Here we go downhill from reactant to product. So when I take product minus reactant, I am going to get a negative value. Plus is going to be endothermic. Minus is going to be exothermic. So let me fill that in. The negative one was reaction 2. The positive one that went uphill to product is reaction 1. Our next question asks, at the same temperature, which one represents the faster forward reaction? A small energy of activation is proportional to a large forward rate constant, which means the reaction is fast. So I essentially need to look for the one with the smallest energy of activation in the forward direction. So while I don't need to look at the diagrams, I could just compare energy of activation forward for diagram 1 is 7, and energy of activation for diagram 2 is 5. The smaller energy of activation forward is going to result in the larger value for the forward rate constant. So that would be 2. What about the faster reverse reaction? The same idea holds. I'm looking for the one with the smallest energy of activation. So the reverse energy of activation is going to be the difference between the product energy and the transition state. So if I take transition state of 7 minus product energy of 3, I'm going to get plus 4. Here I have a product energy of minus 4 and a transition state of 5. So if I take 5, which is my transition state energy, and subtract a minus 4, I'm going to get an energy difference of 9. The smaller energy of activation is the one that gives me the larger rate constant. So diagram 1 is going to have the faster reverse reaction. Our next question asks, which bond is stronger, A bonded to C or A bonded to D? And we're given a hint. Remember, the stronger bond is at lower energy. So AC on this scale is at 3 kilojoules per mole. AD on this scale is at minus 4 kilojoules per mole. The stronger bond is at lower energy, so our AD, which is at minus 4, is going to be the stronger bond. Our last question asks, which diagram represents a value of K greater than 1 or a value of K less than 1? Now, remember that the equilibrium constant is products divided by reactants, and that at equilibrium, more of the reaction components will be on the lower energy side. So what you can essentially do with these reaction coordinate diagrams is think of them as an old-style pan balance. If I had 10 molecules going into this reaction, we know that the lower energy side is favored. So for diagram 1, I might have 4 product molecules, but 6 reactant molecules, because reactant is at lower energy. For diagram number 2, I might have 7 product molecules and only 3 reactant molecules, because product is at lower energy. So if K is product over reactant, for diagram 1, I might have 4 over 6, which is less than 1. For diagram 2, I might have 7 over 3, which is greater than 1. So the diagram that has an equilibrium constant that is greater than 1 is the one with product at the lower energy, which is diagram 2. And the one that has an equilibrium constant less than 1 is diagram number 1, where reactant is at lower energy.